Good morning, good afternoon, or good evening from wherever you're joining us from, and welcome back to the Learn with LINX series. It's fantastic to see so many of you tuning in from all around the world. I recognise a few familiar names, so welcome back. It's great to have you with us again. My name is Holly, and I'm part of the marketing team here at LINX. If this is your first time joining us, Learn with LINX is our ongoing series of free virtual training sessions and webinars bringing together a wide range of industry experts. Over the years, we've covered topics like Wireshark, DNS, BGP, IPv6, and even the fundamentals, like what is an internet exchange and how to use the LINX portal. You can catch up on all of our past sessions anytime over on our YouTube channel. Just search for @LINX Network. Today's session is also being recorded and will be available on our YouTube channel shortly after we wrap up. In a moment, I'll hand you over to our training expert, Richard, but before that, a quick little bit of housekeeping. This is a webinar, so if you'd like to ask a question, just use the Q&A button on your Zoom toolbar. I'll be keeping an eye on them and will pass your questions along to Richard throughout the session, so don't feel like you have to wait until the end. We've explored a wide variety of topics that we hope bring value to the community, but we'd love to hear your suggestions too. So feel free to drop us an email at marketing@linx.net or share your ideas in the chat. It might inspire others as well. We love collaborating with you. But that's enough from me. Richard, over to you. Let's get started.
Thanks, Holly. Morning, everybody. You can see me now, no doubt. Hopefully you can all see the screen as well, which should say, or does say, Introduction to BGP. Like Holly says, if there's any questions, if you pass them to her, and she will pass them on to me, and at some point I'll try and answer them for you. Yeah, so this webinar is about BGP, of course, and if I just move forward a slide or two, a slide being the right one, here you can see the topics that I'm going to be working through. I decided to put the first part in the objectives, the terminology, because there are some key phrases, key words, whatever you want to call them. It's a good move, I think, to get them out of the way at the start, because I will be constantly referring to them throughout sections 2, 3, 4, 5, etc. Possibly one of the key things just to point out in the sections 4 and 5, where we actually get around to, or where I actually get around to configuring BGP and demonstrating it, it will make reference to the messages that BGP uses. And you can see here in section 4 that there are open messages, and in section 5 there are such things as keep alives, updates, notifications. Yeah, so I just thought I'd point that out. So Wireshark, as Holly mentioned in a preamble, it figures quite a bit in this course. Yeah, only purely informative, but yeah, it's there nonetheless. All right, right then. So it's scheduled to last 2 hours. That will include a break about 11 o'clock for a convenience break, shall we say, and then just before the 2 hours we'll finish off and see if there's any questions. All right, so there's quite a bit to get through, so without any more to do, I'll stop waffling and we'll see what we can see. Okay, so here we go. So this is the introduction to BGP, whereby we'll explain some of the properties. We'll see what it has to say for itself. Okay, so here, this is BGP. It is an exterior gateway protocol. Yeah, that means it runs between 2 or more separated networks, exactly like it says here. I'll try not to read the slides as such, but you know, you can't help but do a bit of it. But certainly here, we've got 2 completely different systems here. One could be for the British government, we'll say, other could be for the American government, whatever. You know, and then they are connected courtesy of BGP, running off these edge devices. All right. So border gateway protocol is an exterior gateway protocol. That's the first thing out the way. These networks themselves, if, as I say here, you can see there is the edge router communicating with another edge device over here. Hey. So like I put in my little bit of text there, these routers are on the border of their respective networks. This is quite a big deal. I know it might not seem it, but when these devices are talking to each other, certain things happen. Yeah, you'll see what I mean by that. I don't want to jump into it straight away, but these routers are extremely important. Yeah, they will do their bits and pieces and then deliver information between themselves. All right. The networks themselves, as we have here, hopefully you can all see my cursor. I'm just flirting around this one on the left-hand side. So this network here, it can have multiple routers and probably will have, and they will all talk to each other internally. These run an internal gateway protocol, interior gateway protocol. Yeah, this will be the stuff that you are well and truly familiar with: OSPF, ISIS, maybe RIP, probably not. Maybe ERGRP, probably not. But certainly OSPF and ISIS. So these devices can talk courtesy of the IGP, and then they can have BGP sat on top of it. So that in itself will give you two flavors of BGP. There is external BGP, where the BGP is running external to the network services, or you can have internal BGP, where it is running within your network and making use of whatever services there are being offered there. So, in summary to this slide then, we've got two completely separate systems. When I say separate, I mean they are not related, but they are obviously connected because that's what we've got here. Within each system, there are multiple devices and they will run an IGP for connectivity and more than likely be running internal BGP sat on top of them. Okay, that applies to both. And we can see here, oops, hello, right, there. These networks, they might contain multiple routers, as I've just said, communicating via an IGP. This is quite important you know this, because BGP, the external gateway protocol, the exterior gateway protocol, call it what you like, it will accept input from the IGP. All right? It doesn't matter what the IGP is, could be ISIS, could be OSPF, could be RIP, could be static, could be just connected. But the information will, in some way, shape, or form, be delivered into BGP. So if we did that on this left-hand side here, the information would be generated, would be popped into BGP, would be delivered across here to the target device, the destination device, and then the IGP, the data, the traffic would be delivered into the IGP over here. So this could be OSPF, no problem at all. This one could be ISIS, no problem at all. They can communicate. It could, for that matter, be RIP and static. They will still communicate. Okay. Super importantly, BGP here, it connects to a target device. Yeah. And what we've got going on here, this device is talking up here to this device, and this one is speaking up here to this device, and they are using TCP port 179. That is the BGP port. So if ever anyone's talking about, oh yes, we use port 179, they are referring to BGP. All right. The TCP in itself, Transmission Control Protocol, gives it the reliability for information. Because of, as you know perfectly well, it is a reliable protocol. Okay. So this will be seen, demonstrated, if you like, in the first lab. Yeah, where we're talking about just how things are set up. Okay, so all of this will become clearer, hopefully. This again is a big deal. Yeah, BGP uses different message between the peering devices. Yeah, so these devices are your BGP speakers. They will become BGP peers. They are communicating. They are communicating on port 179. Fine. The messages they use to get the ball rolling are these. They are open, there are keep alives, there are update messages, there are notifications. There are one or two others, notably something called root refresh, but I'll not get too sidetracked into that. What I will get sidetracked into, in this open, right? The devices, the routers, the devices themselves initially are in an idle state, all right? So they are not working. They will then progress through various states until eventually they start communicating with each other and they become established, all right? Now, as that goes on, what I want you to realize, and I'll point this out when I do the first lab, right? In this open situation, this device on the right will talk to the one on the left, the one on the left will talk to the one on the right, and they will, in effect, query each other to try and find out the capabilities of each other. Yeah. In particular, in this, just as a swift example, you could have 16-bit AS numbers or you could have 32-bit AS numbers, right? If you're not sure about AS numbers, it will be here very shortly. So, suffice to say, they can query if each other can handle only 16-bit AS numbers, or can they also handle 32-bit AS numbers? So they are finding out the capabilities. And it's really important you just realize that. There are a few other functions that happen at the same time. Then, having progressed to an open stage, they will start to generate keeper lives, heartbeats, if you like. Yeah. So they will send these keeper lives. They are sent every 60 seconds. You will see lots of these in the lab because they're there all the time. All right. So it's just a question. Device A says to device B, are you still there? Yes, I am. Are you still there? Yes, I am. Fine. Then, so that will be in the first lab. Then the update will occur in the second lab, and that is exactly what it says. Device A could be talking to device B, and a network could come online. So the sender, we'll say device A, could send an update to device B, notifying of what's going on. All right. There are also notifications which we may or may not see. This is when something is pretty much when it's going wrong. Yeah. A good example of this is if you mistype an IP address, if you mistype an AS number, you could start generating notifications because the devices just don't know what you're talking about. If you meant to put, we'll say 192.168.1.0 as a network, and you put 192.168.10.0 as that network, it just wouldn't be able to find it. They wouldn't know what you're talking about. If you mistype the AS number, if you want to put 64512 and you put 64513 or 22, again, it won't know what you're talking about. So this is quite an important slide. Open, keep lives, updates, notifications. We will see them. Okay. BGP here can run within an autonomous system. That's what an AS is, an autonomous system. LINX is an autonomous system. It is a self-contained entity. Fine. It will be identified on the BGP stage with an AS number. And like I've just said, this AS number is nothing other than an identifier. Yeah, it could be 16 bits, 2 to the 16th is what, 65,536. So the identifier can be between 0 and 65535. Fine. Within that range, 64512 and above to 65535 are what they call private ASs, and from 0 to 64511, they are public ASs. All right? The difference being, similar with your RFC 1918 addresses in networking, some are allowed on the internet, the public ones, and those private ones aren't. So there has to be action taken on that. All right? So if we have two ASs here, this one could be LINX, we'll say, this one could be the NHS, and they will peer together to do whatever they have to do. BGP runs within the AS. It does, it can do, and it's called internal BGP, IBGP, and or it can run externally to the AS here, where it is called external BGP. Fine. Now then, something for you to remember. If you're familiar with routing, which I suspect you are in some way, shape or form, the routers tend to have an admin distance, or at least in the Cisco world, they have this admin distance. It again is a number. It is an indicator of trustworthiness. All right. The lower the number, the more trustworthy the protocol, or the more preferred is the protocol. For your information, the admin distance of external BGP is 20, and the admin distance of internal BGP, for a Cisco default at least, is 200. Yeah, other vendors will have different values. Fine. But for the moment, I would like you to remember that IBGP, admin distance 200, eBGP 20. Again, we'll see this. So shortly, actually. There we go. When you are running internal BGP here, or here for that matter, the routers will also run an IGP to build the topology. So this IGP here, like I said a few minutes ago, will more than likely be OSPF or ISIS. Fine. Then, as I put here, it might well be OSPF. Fantastic. Big deal. BGP has attributes. Yeah. There are different types of attributes. You will see them later on, and there are about 11 of these. Yeah. And these attributes, they are what help give BGP its flexibility. You can change things. If we are talking of routing ordinarily, the IGPs all have metrics. OSPF has a metric, ISIS has a metric, so does RIP, and so does anything else. Yeah, so does BGP. But the IGPs will choose the best path according to their metric, right? And you really can't change that, he says, hopefully, but you can use policy-based routing. But you can't change the metrics. They are in charge. Whereas BGP has these attributes. They allow you to make choices that fit in with your policies. Okay? Again, we'll see these later, so don't get worried about it. So, with that in mind, we have a lab coming up now. All right? All I'm going to do in here is enable the router name. I'm not going to bother with passwords because it gets terribly tedious when I forget the password and I can't bother to type them in. So I will enable the protocol and the IP addresses. Okay, although the IP addresses on the interface are pretty much set up. So if you just bear with me, here I am now going to go into the lab, and here it is. All right. Now you can see here we've got an AS64512. We've got a separate AS over here, AS64513. That's the identifying number, nothing more, nothing less. I do have a couple of devices here, well, one actually, I haven't bothered with this one, but here, these are running OSPF in here, and they are also running internal BGP. Over here, we've got two directly connected switches, but again, this device is running BGP, or it will be. It's not doing yet, but it will be. Yeah, and it's going to be talking to this edge device here, in much the same way as I've been outlining. Okay, so if I go onto this device here, this Vios number 1, and have a look to see what it has to say for itself, you can see it's got a router name. Fine, just make that a bit bigger. And if I type in this command, show IP BGP, we should see that BGP is up and running. It is. All right. Now, the first thing to take notice of, it's not desperately important yet, but it will be. Yeah. Actually, there's quite a lot to take notice of here. What I've got within this yellow AS, I've got two devices and they each have a loopback address, 11.11.11.1 and 12.12.12.1. And you can see here, they are in the BGP table. Fine. There are routes to get to these two networks. Fantastico. And what it does, BGP will highlight what it thinks is the best route. So I just want you to realize that that chevron there, not the asterisk is saying the path is perfectly valid, but that chevron is saying the best way to get to 11.11.11 is going to a next hop up here, yeah, to an IP address. And it just so happens that this one here, the network address is 200.1.1.12/30. So you've got .13 at one end and .14 at the other. So that's pretty typical of routing, actually. But look here. Here, these are some of the attributes, all right? These are going to be featured a lot throughout the course, yeah? There is the metric, which, as you can see, is set to 0. There's something called the local preference. There's another thing called the weight. Fine. And then there's this mysterious thing at the end called the path. These are attributes, okay? Fine. So there we go. That's that for the moment. So if I now just close that session off and go on to this one here, there is, and I type in show IP BGP. Oh, tell you what, try and spell it right, BGP. And it says BGP is not active. That is quite right. So I have to turn BGP on. To do that, I will type in enable. That will put me into not user mode, configuration mode. I will then do config T, configure now. So now well and truly in the configuration mode. And I want to type initially the routing process. The routing process has a number 64513. You can see it matches the AS. So now router BGP 64513 is up and running. What I have to declare now are the networks that I want advertising or that I want to announce. All right. And I've got 192.168. You can see I've got 192.168.3.0 and I've got 192.168.4.0. So if I just put those in, 192.168.3.0, fine. I need to put the mask 255.255.255.0. Fantastic. And with a bit of luck, I'll be able to type 4.0 before anything else happens. So they are both announced, capable of being announced now. Now then, hopefully you will remember that this device here communicates with the device over here. So in order to get that ball rolling, they are going to use external BGP. All right. So we are going to configure BGP now. And it's reasonably straightforward. All I have to do is declare the neighbors I am talking to. And you can see here, I've got a subnet 201.1.0 on the top link, and I've got another one 201.1.4 on the bottom link. So this is going to come from 0 to 3 using 1 and 2. This is going to go from 4 to 7 using 5 and 6. So I will put in the neighbor. Whoops, never could spell. I'll put in the neighbor like so, and I'll put 200.1.1.1, and that is in the remote system. That is the syntax. It's always remote AS. It doesn't matter even if it's in the same AS, it's still a remote AS. And this one over here, as we could see, is 64512. So 64512. Now, if I had mistaken put 64521, that would have caused a bit of a flap in BGP, yeah? But I haven't. So I'll just press enter, and hopefully it will recognize what I've done reasonably quickly. But if not, I will also type the next line, and I'm just going to do the bottom link now. Look at that. I knew it would do it as soon as I pressed enter. Let me just do this. So now I'm going to put 200.115. Fine. This is the bottom link here, and we're going to have another BGP change. All right. And I've just realized I meant to do something before that. Blast. Right. So what I'll do, I'll just get rid of that one. No neighbor. And I'll also get rid of the other one. No neighbor. DTTT. There it is. No neighbor. Right. So that's got rid of that, and it's broken the connection. So just to check what I've done, do show run. Just have a look at the running config. It's only take a few seconds. There we go. Right. And we should see within my config here, I've got BGP there, and I have only got really the networks described. Yeah. So I will do no network, 200, no neighbor, sorry. Brief. 200.1.1.5, remote, AS 64512. And that has broken the BGP adjacency, so that is good news. Right, what I'm going to do now, I'm going to shut down interface number 3 on this device here. So interface gig 03, fine, and I'll just type in shutdown. Done. Right, now what I want to do is this. I'm going to go onto this device and I'm going to turn on Wireshark. Okay, so I've turned on gig 3, I want to use gig 0. So if I say I want to capture the information here on gigabit 00, Wireshark springs into life. Maybe not springs, but gets into life, and we'll get ready. There it is. So Wireshark is up and running. Good for it. Now what I want to do is just go back onto here, and now I'm going to put those networks back into BGP. All right. So I'll do exit, and I'll type in router BGP 64513. Fine. And I'll put my neighbor 200.1.1.1 in remote AS 64512. There. And I will also put network or neighbor 200.1.1.5. There it is. Just making sure I take that right. So now you can see what's happened, right? There has been an adjacency formed between VIOS 2 and VIOS 1, and it is using the IP address of 200.1.1.1. Fantastic. There will also be one on the 200, there it is, on the 200.1.1.5. So what I said earlier is that these BGP devices, they will start to talk with each other using these open messages. So all being well, if I go into Wireshark now, and we could say, I want to see any BGP information here, there it is. Now look here, this is the open messages, you can tell because it says open, right? What you can also do, chaps, for your information, in here, in Wireshark, for you experts, if you type in BGP type, yeah, you could then put equals, and if you put a number 1, it will only show the open messages, all right? If you put a 2, it will show the update messages, and if you put a 4, it will show the keep alive messages. And if you put an 8, it will show any notifications. There probably aren't any just yet, all right? But if I go back to my BGP, here are all these messages. Now, in my preamble on the previous section, I was saying we're going to have a look at that. We're going to do it now. So I'll just move these boxes across a little bit. So I've got a tiny bit more space, maybe. There we go. And if I bring this just up here a little bit. Right, there we go. And you can see, as one would expect, you've got all the different layers of the OSI model down here. You've got layer 1, layer 2, layer 3, layer 4, we'll say layer 5, 6, and 7, right? Now you can see here, look, the internet layer 3, the source was 200.1.1.1. It is in this case, fine. So let me just scroll up a little bit. So I've gone onto this device here. The source device was 200.1.1.1 talking to 200.1.1.2. That's fair enough. What we're interested in really is here, look, yeah? In TCP, the source port is 40506, if you say so, yeah? And here's the destination port, 179. You will remember that from the preamble. I said BGP uses port 179. If we have a look at the other side of the argument, we will find here that the source will become 200.1.1.2. It has, and it's talking to a destination 200.1.1.1. And now the source port, BGP talking back, is 179 to that. This is great news. So things are rolling. The ball is rolling. If we have a look into the open message itself, right, a thing you need to be aware of here, this FFFFFFFF is common to all messages. It's always there, right? And that's its length because this will vary because due to the amount of data that can deliver between the different messages, all right? And it says here, there is an open message. There's one, yeah? It's type 1. There is one of them. It's running BGP version 4. It has come from my AS 64513. It has. That was the one on the right-hand side. It has, all right? It tells you that the hold time, this is the hold time for the keeper lives. So basically, we are exchanging information and we are saying to the recipient, look, I am from 64513. I am going to generate, it doesn't say I'm going to generate keeper lives, but it says I'm using a hold timer 180 seconds. If you divide that 180 by 3, because that's the standard, it will give you 60 seconds. Your keeper lives are generated every 60 seconds. And so it goes on. There is a BGP identifier on here somewhere. Fine, 201.1.6, fine. But what I'm really interested in, if I come down here, there are these optional parameters. And look here. This is what I was telling you about. We have optional parameters. Can you do this? Can you do that? Can you do this? Can you do that? And if we look into them, it tells you you've got multi-protocol. There is multi-protocol BGP. So basically, in this open message, this is really important, this. In the open message, the source device will say, can you do multi-protocol BGP? And the destination device will reply accordingly. Then, if we just see what else there is in here, there is now this route refresh. There is an automatic capability in some systems. Yeah. What you have to realize again, BGP is policy driven, right? Your policy might be that you want to filter all of the traffic coming into you and you only want to allow 192.168.10.0 networks. That's fine. That's fine. That is your policy. You adopt your policy, you adapt your policy to the BGP syntax. You set it up on your routers, right? And that's that. Then when you change your policy, i.e. when you change your configuration, you need to tell the interfaces, yeah? Otherwise, the changes might not be adapted straight away or adopted straight away, all right? So this here, this is a big old deal. Here, let's just see what that one is. It's the route refresh capability. I think I've clicked on the same one again. And then it goes on, just discussing capabilities. That's fine. There is an enhanced route refresh capability. And this is the last one for the moment. Look here. Now it's saying, can you support 4 octet? Well, of course, an octet is 8, 4 8 is 32. That's your 32-bit AS number. So this is bearing out exactly what I was saying. The open it needs a lot more credit than it gets. It does a lot of different jobs. Okay? So there we go. Then from there on, we've got the keeper lives. BGP type equals number 4. There we go. And the keeper lives, dead straightforward, but there's something I want you to see. Here, look, there it is. Like I said, the messages always start with all the Fs. That is padding, if you like. And it tells you here the keep live is type number 4. Fantastic. There's nothing to see. It's just literally waiting for a command. Okay? Simple as that. So that, with a bit of luck, that would have been quite interesting for you. What I'm going to do, I'm going to stop Wireshark now, because I've finished with it. And if I go back to this now, because we should have some kind of neighbor relationship going on, and if I type in here on this one, let me just move my Vios 2 out of the way, I will go on to Vios 1. I haven't got one, fair enough, so I'll open a session on Vios 1. And now, if I type in enable again, and I type in show IP BGP, we'll see if there's any change to what the syntax was previously. And we can see we've still got our 11.11.11.12, all of that business. Fine, because the interfaces haven't come through yet, as yet. So that's fine. If I now do this, I type in clear IP BGP. What that's doing, that because on the other side, I made some changes and I put the neighbors and I put some networks, I changed my policy. So now I'm going to inform the interfaces, in effect, that I have changed my policy. That has now generated a notification, look, and it has said, look, we are resetting ourselves. They reset the neighbors, and if I quickly type in show IP BGP, there's not much there yet because the neighbors haven't all been validated. There is validation of another neighbor, 200.112. It's used syslog with a notification there. So if I type in show IP BGP now, we should see that we get it started to get the information coming through. Okay, so I'll have a look on VIOS 2 as well. It can take a short period of time to show IP BGP here, there. So it's got those networks in there, fine. And over here, so now as I type in show IP BGP summary, and we'll see what we've got there. So now this system here has 200.112, fair enough. It's got 200.116, and it's got 200.114. Those are the interfaces applicable to my system in itself. And if I type this in, show IP root, right, there we go. So that's, oh, sorry, I want to type in actually show IP root BGP, and we'll see what we've got. As yet, nothing, yeah, because I haven't finished the whole job, okay? But that is the first part of that lab completed, yeah? If I just do show run on BIOS number 2, we should find go down to the BGP, and you can see in there we've got that kind of information. Yeah, network 192.168.3.0, network 192.168.4, and we've got the 2 neighbors already set. Good. So finally, I want to now do show IP interface brief, and we'll see which one is down, and I'll now turn on interface gig 03. Interface gig 03, fine, no shut. That has now brought that information to life, that interface to life, I should say. You can see the interface has come up and life is looking pretty reasonable. Look at that. There is another BGP adjacency now. Yeah, so we've formed another adjacency now. OSPF has kicked into life as well and recognized everything is there. You show IP BGP now. Now look here. This is a big deal. Again, this is the BGP table, and I really want you to have a good look at this. All right. You can see now that on this particular router, this one here, this one, right? You can see to get to 11 dotted. This is dead important, chaps. All right. If anybody's feeling a bit tired, this is not the time to go to sleep, right? So we can get to network 11.11.11.0, and we have 2 paths available. Well, there are. Of course there are. We could go on this top link, or we could go on this bottom link. And you can see here, again, you've got an asterisk saying that, yes, the route is live. Good for it. But on the second one, it's got that greater than sign again. And that greater than sign here is, as far as the routers are concerned, that's the best path. So the information is going to go along that path. And you can see its next hop address is 201.1.1. It's going to go on the top link. Then it carries on. It goes through these attributes. And you can see here, yeah, there is something in this AS path attribute now. And it is the information, it's telling us where this information has come from. So this information now about network 11.11.11 has come from 64512. It has. That is ridiculously important because what it's saying is that 64512 is the source of that information. It is. Yeah, it is. That's where it's come from. And the same thing here, we have 12.12.12, which is somewhere on this device. But again, it's still in 64512. And you can see again, that in this case, this is the top route is a preferred route. And again, that information has come from 64512. Fantastic. Okay. There are also, again, super important, there are also, as far as BIOS 2 is concerned, this one, there are two networks, 192.168.3, there are here, this one, 192.168.3, and there is another network, 192.168.4, here. Now what this is telling us, look, if that particular device 2, BIOS 2, wants to get to 192.168.3, it doesn't have to leave the AS. So there isn't a next hop. It stays within that AS. Fine. That is indicative of a local network. All right. Similarly, it also has this weight set to 32,768. You might remember, it depends on what you know. That is the same weight as spanning tree for what it's worth. But the combination, if you like, of 32768 and the quad 0 next hop means it is a locally generated network. Fantastic. All right. So that might be your first look at a BGP table. I don't know. You might have seen it millions of times. I don't know. You know? But what I do know is that where there are multiple paths here, BGP will pick what it thinks is the best path. And it will start to use these attributes here as we go through the course. Okay, so there you go. That's it for that lab at the moment. So if I drop that out of the way and go back to here. So that was that lab. All right. I didn't configure route names because I'd already done it. I haven't put passwords on because I can't be bothered. But the routing protocol is up and running. Fine. We now have this, talking about networks and the internet. All right. End of the chapter, you'll be able to explain some types of network and talk about the internet to an extent. Okay. So here is a network. I know it might not be the most glorious or the most complex. Again, doesn't matter. What does matter is that there are at least two routers here. Yeah. This router here has an interface in this network. It also has this interface in this network, going through this router here, and then it's got a switch over here, and again, it's a network. So there are 1, 2, 3, 4 networks here. I tend to call them broadcast domains because I like the sound of that phrase, But the fact of the matter is that using these, all of these devices within a network can talk to each other perfectly happily. There is no problem at all talking to each other within this broadcast domain. Similarly, down here, we have another broadcast domain. All devices in here can talk to each other, as indeed so can these. But if these want to talk to somebody else in a different broadcast domain, they have to leave the system. They have to go through this default, this exit interface, this egress interface, this default gateway. Yeah, this gateway. A gateway is a way out of a network and it can start to go wherever it has to go because the routers keep all the links available. They know, this router knows that this network is here. Yeah, because it's plugged into it. It knows that this network is somewhere over here because they have gleaned the information, and this router here knows that this network is here because that's how they work, and we'll see it in action. Fine. So, like I say, at the risk of being boring, if this device wants to talk to this one, it just can. If it wants to talk to this device here, it would need to egress on this interface here, pass through here, pass through here, and pass through here. And these routers will have built the tables on received information so they know where each network is. And when I say they know where each network is, I mean they know which interface it is connected to. Fabulous. So how do we do this then? Well, we could use our networks. We have them here. It could be a wide area network. Yeah, absolutely. It could be in a warehouse. It could be in a block of flats. It could be in a block of offices. Doesn't matter. But the sites, they will be connected by either a dynamic routing protocol, ISIS, OSPF, RIP, etc., IBGP, static routes. Fine. That's how they can communicate. The wide area networks are geographically unconstrained. Yeah, it's not like talking to the office next door. You could talk, as I'm based in Leeds. Yeah, we could talk to someone in London or someone in Stockholm or someone in Berlin. It is not geographically constrained. Fine. And there's the internet. Never catch on. But there we go. They've got multiple service providers or whatever these are, ASs, autonomous systems. And again, they have multiple devices. And you can see that there are edge devices always. So these will be running external BGP in order to exchange information with each other. And this is how the system works. There are multiple ways the internet are connected. You can see here we've got a little bit of a schematic on some undersea cables. Fine. Yeah, so there are those. Big deal, big deal. The routers forward packets what they think is the best way. Yeah. So from here, they could this system, just for example, might think the best way to get to this one is coming through here. Fine. If it does, good for it. They might think that this is the best way. Well, it's certainly shorter. That's good news. The routers will do this automatically. The routers, if you prefer them to be called routers, fine, routers. Yeah. So these routers, they know this is the best way. But BGP, your policy might be that, hey, look here, this customer who wants to be up there, he doesn't pay us very much money. So we will send him on a more circuitous route. Yeah. This is one of the things you can change with BGP. It's one of its big advantages. But routers forward packets what, in their opinion, is the best way. This is how they do it. You can see here what the routers do. They forward layer 3 packets, layer 3 from the OSI model. They use the destination IP address. So we can see here, if I just move my thingy out of the way, we can see up here on this top link, gig 02, somewhere out on gig 02 is a network 172.16.1. Fine. These devices have all spoken with each other. They've all spoken with this one. They all know the state of everybody's interfaces. Fine. So this device here, this central one, is sending a packet. It is going from itself, 10.1.1.1, and it is going to 172.16.1.2. Now we can see pretty clearly that 172.16.1.2 is up here on gig 02. But the router doesn't know that. No, all it knows is that it has to send the information at least on its way. So it will look at its routed table and it will say, aha, network 172.16.1, that's the one I am looking for. And it says it is somewhere on the edge, it is somewhere connected to gig 02. So the router will send it out of gig 02 over here. This router will then receive it. It will have a similar routing table, and it will also see, by an amazing coincidence, that this 172.16.1 is actually on gig 02, and it will send it out of here. Life is good. Yeah, you can believe that if the destination network was 110.1. something, yeah, well, it would be a member of this network, and it would be sent out of gig 01 here. And of course, if it was a member of the 172.31.8 network, it would be sent out this interface down here. They do a little mathematical calculation, which in itself takes about, oh, I don't know, 2 nanoseconds or something ridiculous like that, you know? So these routers perform these calculations, goodness knows how many times per second. Fantastic. And there's our routing packets now, all right? So you can see that routers forward packets the best way. We can see here that, yeah, fair enough. This device here could receive incoming information. Again, it's testing for 172.16.1.2. This router will say, aha, I can send it that way to this router, or I can send it this way to this router, yeah, and then up there. And again, it just picks what it thinks is the best way, and it uses these metrics. You will be aware that OSPF, it uses something called cost. Fine. RIP in itself uses a metric called hop count. And if we was using RIP in here just to illustrate the thing, yeah, RIP would say the data would leave here. It would then hop over one interface. It will hop over one router, and it's there. That's fine. Or I could send it this way. The information would hop over that one, which is one hop. Then it would hop over that one. So that's 2 hops. Well, 2 hops is inferior to 1 hop. So the router would think that this is the best way, the path of least resistance. RIP doesn't use bandwidth. It doesn't come into it at all, whereas OSPF and ISIS do. So suffice to say that routers forward packets what they consider to be the best way. Okay. So who updates these routing tables in the routers? Well, we can. We can use static routes ourselves. All of the interfaces are configured with an IP address. Fantastic. It has to, it's an identifier again, and it assists with routing the information. Absolutely right. We can update the routing tables courtesy of static routes that we set up. Perfect traffic engineering, if you like. Static routes works perfectly well. Or we could use routing protocols, IGPs, EGPs. We could use both of them. The downside to static routes is if you set up a static route, you must configure some kind of alternative route, because if the static route you configure fails, you are in a problem. Yeah. Whereas the dynamic routing protocols, they would pick the best path and they would pick alternative paths as well. So routing protocols, bigger networks, static routes, perfectly okay for a small network where there isn't a great deal of activity, really. Yeah. Here, a little bit of an update on the protocols. We've already covered this. Routing protocols here. There is an autonomous system number, 64512. That is a private AS. They are running an IGP. No problem at all. No problem at all. So the internet sites do have an AS number, and that's the range. 065535, 65536 in total, 64512 to 65535 is the complete range. IGPs run within here, and EGPs run here, and they will correct separate ASs. Fine. And there we have it. There's confirmation of what I've just said. All right. So in here, we've got 64513 down here. Could be a service provider, or it could be a customer of a service provider. Absolutely right. This one up here, we've got a service provider. The AS is 3100. If it is, it is. We've got another one over here. This one is 4100. These are external BGP. Why? What actually makes it external? Well, it's the fact that 41001 is talking to 3100. 3100 is not the same as 41001. So they are running external BGP. Similarly, 3100 is not 64513. So again, because they're not the same, they run external BGP. Whereas if these routers here are all running BGP, that would be internal BGP, and each one of these devices is a member of 64513. So consequently, this speaker speaking on behalf of 64513 would speak to this one, which is working on behalf of 64513, as is this one, as is this one. So these would all be using iBGP. Okay, fine. There we go. Let's just see how we're doing for time. Just bear with us. You want to, Holly will tell us. Hey there, Holly.
I am. It is just about to turn 11 o'clock.
Right. Do you want us to stop for a break for 5 or 10 minutes then?
Yes, let's all come back in 5 minutes, so 5 minutes past the hour for part two.
Excellent. Thanks, Holly.
Now that is 5 minutes past the hour, so hopefully we've all had chance to go and get ourselves a cup of tea and ready for part 2. Remember, if you have any questions, please use the Q&A function in your Zoom toolbar to ask those, and then we can get those over to Richard and answered for you. But there we go. So let's settle in for part 2.
Great stuff. Thanks, Holly. Right then. So here it is then, part 2 of our journey through BGP land. So with what I've just been saying there, if I just drop into my lab again, and we just have a look at another few bits and pieces, all right? Now, what we've got on this device here, fine. On this device here, we have got a connection, got 2 connections actually, to this AS over here. So that means because we are going from 64512 to 64513 and vice versa, yeah, this is running external BGP. Then we have a device in here, which is also a member of AS 64512, as indeed is this one, as indeed would this one be. So these are running internal BGP. So now, if we are curious, we could go onto this device here, and I could just type in, show IP BGP, of course I could, because we've seen that. That will show me my BGP table. And we can see that, actually, there is a network somewhere over here on, let me just move it out of the way a little bit, 11.11.11.0. There's another one, 12.12.12.0, and there's 192.168.3. Well, we can see here that actually 192.168.3 is over here, as indeed is 192.168.4. So these are actually contactable via external BGP. And we can prove that because if I make that a little bit bigger again, and this time I ask to look at my routing table, show IP route in table, and I will put BGP. Yeah, because I'm interested in BGP. That's what I'm particularly curious about. So I'm going to press enter. Oh, never could spell show. Show IP BGP. Now look here. It tells me a few bits and pieces. All right, the gateway of last resort is not set, not bothered, not interested. What I am interested in is that, look, I could use BGP here. I just make that a little bit bigger. We can see somewhere up here there will be a B for BGP. Can't see it, but it'll be in there, a B. BGP, there. So we've got B for BGP. And we can use BGP to get to 11.11.11. So what? Well, the so what is that this is all in 64512. So we are using internal BGP, IBGP. And if you remember, I said the admin distance of IBGP is 200. And there it is. It says, look, you, number VIOS1, can contact network 11.11.11.0 using internal BGP going via the next hop of 200.1.1.14. Well, it is, because we've got a subnet 201.112/30, so that goes from 12 to 15. This will be .13, and that'll be .14. That's fine. Then it also goes on to say, and I tell you something else, Mr. VIOS1, you can get to networks 192.168.3.0 and 192.168.4.0 using a protocol with an admin distance of 20. Well, that's external BGP. Yeah. So the system is working quite happily. Yeah. We have internal BGP working here within 64512, and we have external BGP working quite nicely, thank you very much, between 64512 and 64513. And hopefully we should be able to ping 192.168.3.1. Fine, we can ping 3.1, we can ping 4.1. Fine. Can we ping 11.11.11.11.1? I don't know. We'll soon find out. Oops. Fine. So the system is working. Fabulous. Okay, so that's all this good news. So I'll just whip that back up here again. I'll go back to my show IP BGP. summary again, just so we can see what there is going on. And we can see that, sure enough, we have all of our neighbors in quite the right place. Okay, show IP BGP. And there we have everything quite happy. Okay, good news. So we'll see what happens next. A little bit on ASs themselves, not too much, but a little bit. And here, this is where it's starting to get interesting, all right? Because within the ASs, you have these policies. I've already said BGP is policy driven, and a policy, yeah, it's a written document, there's no doubt about that, but that written document will contain all the parameters for your working. And in this case here, it just gives you might say a trivial example. Yeah, the policy is that router 1 chooses to announce 10.000/8. Fine, fine. If that's its policy, that's what it does. Fine. AS64512, it does have network 10.000/8, and it chooses to announce it up here. Router 2, its policy, it chooses to accept. So that's its policy there. Yeah. So this is quite a good setup. One is wanting to send 10.000/8, and the other is choosing to accept 10.000/8. Fine. There is a little thing just sneaking in here, which could easily be overlooked. And it says router 2 chooses to accept 10.000/8 from AS64512. What do I mean by that? Well, if I just jump back into my lab, just for a minute, here, and I put in that very last command that I just typed, look, we can now see that here, this device wants can get to 192.168.3.0, and we can see that it has come from 64513. So now, that means that surely, if we can program these things, surely we can maybe say, I will accept 192.168.4, but only if it comes from 64513. If it comes from 64512, it's not a valid route. This is a big deal. This is where the policies come in. 192.168.4.0 could have come from anywhere, but we don't want it from anywhere. We want it from a specific AS. All right? That's what we are building up to in the course notes. Okay? So here. So the routing policy, R1 chooses to announce 10.000/8. It does. This one chooses to accept 10.000/8 from 64512. Don't lose sight of that. It will be back sooner or later. There. We now have another example here. We have a routing policy. Yes, our routing policy is we might only have one prefix. Fine. So we might have that 10.000/8. But then we can have multiple sub-prefixes within there because, of course, they will always spawn from the 10.000 prefix itself. Fine. We might have one or more IGPs. Why not make life awkward for yourself? You know, but it might be that we've taken over another company. They just happen to run OSPF. We run ISIS. They run ISIS. We run OSPF. So you might have multiple protocols, whereas your policy originally stated we will only have one IGP. But things change. They are fluid. The AS numbers themselves, good heavens, these are all allocated by the registrars. Yeah, there is IANA, there is the regional internet registrars that look after us. Ours is RIPE, there's AfriNIC for Africa, there's PacifiNIC and LatinNIC, you know. But we can see here, look, the numbers are very near exhausted. Yeah, AS numbers are finite, they are indeed, and they've gone up. Okay, there is that concept of private AS numbers, which helps preserve the numbers, 64512 to 65535. It works really in a similar process to the RFC 1918 for your private addresses. 10.000s, or anything that begins with 10, 172.16 to 172.31, and then 192.168. Yeah, so there it is. This is the look of a 32-bit number. You can see here, yeah, the 16-bit number, 16 bits, 2 to the 16th is 65,536, 0 to 65535, fair enough. There's our private range, 64512 to 65531, sorry, to 65535, as I have said many times. Then there is a transit AS here, number 23456, doing what transit ASs do. Contrast that with the 32-bit numbers. Look here, that is a spicy range. 0 to that is a good old range in a real number. Or you could split it into two 16-bit numbers, where the first bit depicts your AS, and then the second one depicts something else. You know, they've still got a private range, 42, whatever that is, up to there. So, suffice to say, there are 16-bit AS numbers, and there are 32-bit AS numbers. Suffice to say also, we now know that the open message, when BGP is open in negotiations, they will check to see if the peering device can use 32-bit numbers. There's no point using 32-bit numbers if it doesn't recognize the damn things, you know? So there you go. So this is the internet today, potentially. We have lots of service providers here, all connected with BGP. Absolutely right. Perfectly, works like a charm. There is this, good heavens, active BGP entries, good heavens. We're up to 2024, and you can see here, look, the active entries in the FIB, the Forwarding Information Database, yeah, there is a lot, near as damn it, 1 million. Of course, it will have gone up a little bit. So, again, there is a lot of strain here. If you are using a full BGP table, you need some really heavy routers. Lots of processing power, lots of memory to get the job done. Fine. So there you go. Okay. The basic BGP. We've already looked at this, actually. Here, what is BGP? It is an exterior gateway protocol. It builds routing tables. Of course it does. Yeah. IGPs, there are the examples, RIPI, RGRP, OSPF, etc. They also build routing tables. They are the way to find things. They use to find destinations. IGPs work within an AS. EGPs work between ASs. Absolutely right. They are identified by an AS number. What's the pros and cons of each of them? Well, the IGP, broadly speaking, is a lot quicker, yeah, than BGP. BGP is built for speed. It's built for reliability. It's not built for speed, sorry. It's built for reliability and scalability. Whereas IGPs, they are built really for speed. The quicker, the better. So you have a topology with an IGP, notably OSPF or ISIS. These are both linked state protocols, and they do the job admirably. BGP sits on top. Fine. And this is what goes on. So now, just in case anyone had forgotten, I decided to put in BGP uses TCP port 179. Absolutely. So these external devices here, they will send information in to us. This will hit our BGP in process. Our policy will dictate what we are going to allow in and what we are not. Consequently, anything that is allowed in is accepted. It is brought into the BGP table. Fine. If we then have multiple routes to that same destination, this is exactly what we have in my lab. Yeah? All right. It's only 3 or 4 routers, and I've got networks 192.168.3, 192.168.4. They are coming in to VIOS 1 device, and it can realize that, yeah, there are actually multiple routes, potentially. So anyhow, the information will come in, it will be filtered. Yeah, I only want to accept 10.000/8 from AS64512. Fabulous. Yeah, gets all the routes, and then these routes are filtered again. The best routes pop into the routed table. Absolutely right. And then the rest of them can go on their way. You know, they might be exported elsewhere. So this is the BGP process in itself. And there we have it. How do you add routes to the BGP table? Well, these are the kind of routes we can add: connected, static, or dynamic. Yeah. In my lab, if I just drop into it, just for the sake of example, if I go into the lab now, here, there it is, and I type in show IP route, there, we can see there are lots of examples. And we can see not only is there BGP in here, which there is signified by the B, but there are a few OSPF routes. Fine. There are directly connected routes. Absolutely. There are local link routes. So there are a lot of them. But this is a BGP course, so it's BGP that we're interested in. And there we have it. Yeah. 11.11 internal BGP, admin distance 200, 192.168.3. These are both in AS64513. They are external BGP, so they have a smaller admin distance. So there you go. That was just to show the routing table. Right. So we can use these. We can use directly connected routes. They are plugged into the thing. We can specify static routes, or we could use a dynamic routing protocol. We can indeed. That would signify the routing table. Then in the BGP table, which is the one we've been looking at most of the time, yeah, it will use it's dynamic. Why? Because you're getting information from BGP neighbors. They will come in from that routing table, and we can use these network statements. That's what I used. I used the network statement, network 192.168.3.0, mask 255.255.255.0, network 192.168.4.0, mask 255.255.255.0. Fine. There is this, we've not mentioned this. There is redistribution. Easy for me to say. Yeah, this is where we have different protocols. Yeah, and we want to merge them into BGP. So we can redistribute static into BGP. We can redistribute OSPF into static, into BGP, sorry. We can redistribute ISIS into BGP. We can redistribute anything into BGP, and vice versa as well. So that's how we do it. BGP is standard. There is a big section coming up on this business. BGP is standard. Cisco have their flavor of Unix. Yeah, they have their flavor of BGP as well. So does the Barclay Internet Routing Daemon. So they have their own flavor of it, as indeed do Juniper. But they can all coexist. How does that come about? Well, it's because that Unix does have certain parameters. You have to use certain syntax, and it works. So this is the configuration of a couple of devices. This is exactly what I did. On this device, we've got routed BGP, the AS number, 64512. Over here, of course, it's AS 64513. Absolutely. Specify the networks that are directly connected to it. Network 10.00, and then the subnet mask. It's best to type the subnet mask, but if it is the default subnet mask, like it is in here, which is a /8, you could get away with just omitting it. So you just put network 10.000. But it's a good idea to get in the habit of typing it in. So 10.000 mask 255.0.0.0 is fine. Over here, network 192.168.0.0 mask 255.255/16, that is fine. And then we just specify our neighbors. Neighbor 172.16.1.2 here is in remote AS 64513. It is. And this one, by default really, neighbor 172.16.1.1 is in 64512. This will get the BGP ball rolling. Yeah. If you mistype this, the AS number, if you mistype the IP address, it won't work. It will generate a notification that you've done something wrong. And it's reasonably easy to fix, but it's a bit of a bore, So anyhow, There we have it. Router BGP enables BGP itself, sets the AS number, it does indeed, and goes into the router mode. Absolutely. Dead straightforward. Setting up the neighbours, exactly as I've just said, neighbour 172.16.1.2 is setting the IP address of the point of contact here. Remote AS 64513, absolutely. You do it in the router mode itself and it builds sessions. TCP sessions, of course, yeah, and of course it uses BGP port 17, or should I say TCP port 179. And there's your network commands. Network in the router, config router prompt, network 10.00 and the mask, fine, that's it. And that specifies which networks are to be announced. They don't click them into action, they just announce that if you want to get to this network, you have to come to me. And there we have it. And these are some troubleshooting commands. Show IP BGP shows your routing table. Show IP route shows the routing table. And ideally, show IP route space BGP would just show the BGP routes, as indeed would show IP route space OSPF. Right. There's a show IP BGP summary and show IP BGP neighbors, where of course these are neighbors of each other. Okay. And here they are again. I told you they'd be back. So here are the message types. They all have this 32 bits. There's 4 octets there. There's 4 octets there. There's 4 octets there. There's 4 octets there. So there are 16 octets full of Fs. Yeah. And this is what I took pains to show you when we first started. Yeah. And you can see here, specified under the RFC 4271, it says that the open message is a type 1. The update message is a type 2. The notifications, they aren't. They are type 8, as it happens now. Yeah, but the keep alives are 4s. Quite why that says a 3, I don't know. That should be 8. Then, as new updates come out, you remember the open, where they just interrogate each other to see if you could do 32-bit AS numbers, root refresh capability. It just so happens the root refresh is a 5. So 1, 2, 8, and 5. But these are the message types themselves. We saw them in Wireshark. So we've actually done this. This configuration exercise is done. We have it all up and running fantastically well, if I say so myself. You know? So how does BGP work? All right, that's the question. So here, the devices, they will negotiate the peering. They will check out to see the capabilities of each other. 172.16.1.1 will associate itself with 645.1.3. 172.16.1.2 will associate itself with 645.1.2. Fine. They will move through the different states. The devices initially start in the idle state. They will then move through various other points of states, and ultimately they will get to the established level. When they are established, they have exchanged the routing tables. Yeah. So here we have it. Negotiate the peering. They will exchange the routing tables. Of course they do. Yeah. They will periodically check if the peer is still there. The keep alives. Yeah. The keep alives. The hold timer, whatever the hold timer is, you divide it by 3 and you get the keep alive. The default hold timer is 180 seconds. Divide by 3 is 60. The keep alives are generated every 60 seconds. Yeah, fine. Are you there? Yes, I'm there. Are you there? Yes, I'm there. Are you there? Yes, I'm there. On a change, there is a change. There is an update. The updates are generated. Within there, they will have all the information as to what that update entailed. Fine. And here is those messages again. Yeah, so this is message types. Again, we've already seen them. Here are the states I was just talking about. What's important on here is this one. I mean, they're all important, but your devices, they are dormant. They aren't doing anything. The BGP process cuts in. They go from idle. They try to connect with a peer. If they connect with a peer, fantastic. They will then send the open What's the open? It's the open message. They send an open, all right? Then one of two things can happen. The open can actually get to this device, which is good news, or it cannot, because in our configuration we have mistyped something. If you mistype something, the connect won't go to the open sent. Instead, it goes to connect. Instead it goes to active, because you have mistyped the AS number. You have mistyped the IP address. There might not be a cable in the stupid thing, so you're not connected. So it will go to active. Active is not a good state. It doesn't mean it's active, it's up and running, it's working. It means it's up and it's actually looking to make a connection with someone. It is actively seeking to make a connection. So it just cycles round and it won't go anywhere until you fix it. But assuming things do happen, the open is sent. There is then an open confirmation between the two devices, and they will then progress to the established state. Fine. And the established state, if we just have a look at this now, I'm just going to drop into the lab again for a minute. Here, go into my lab now. Oops, missed. There's my lab. If I type in here, show IP BGP, we can have a look. And I don't see any mention particularly of established in there, not really. And if I type show IP BGP summary, I can't really see anything about an established status in here. Now, there's no mention of it, really. But if I type in show IP BGP neighbors, there is an awful lot of information coming up here. You can see here, look, this baby has a BGP neighbor number 200.112. It does indeed, because it's VIOS 1. VIOS 1 here, this is 200.111. This interface over here is 200.112 in that particular subnet. So it has a neighbor 200.112. Fine. And you can see here again, it tells you the remote AS number, 64513, absolutely. Tells you the BGP version is 4. You might remember that from the open sent. I am running BGP 4. Everybody runs BGP version 4. It works. There is a router ID. Yeah, this again, in standard practice, it will default to the highest active IP address or the highest loopback. And then finally, here, there is the BGP state. It is established. Yeah, so this is good news. And if you keep looking, there is the hold time look, 180 seconds. There's the keep alive, 180 divided by 3 is 60 seconds. It then goes on to tell you, right, look here, we have a neighbor session. We have one active session, not one active system, an active session. What can the neighbor do? How about this? Look, this is quite something. It's the neighbor capabilities. We saw that in its open message, do you support root refresh? Yes, it does. Do you support a 32-bit AS number? Yes, it does. Do you support the address family capability there and the enhanced? So this is all what it does. Absolutely superb. So there you go. All right. I just wanted to show you that it was the established that I was particularly interested in there, and we just happened to get a bit more information as well. Okay. Okay. So that's that one. Here. So there it is. So the open sent, the open confirmed, established is the thing you're looking for. And again, we've seen that quite happily, it works. Okay? Good stuff. Now, this is the serious thing, or one of the serious things, all right? BGP, you can influence the path selection. Okay? Fine. And how do you do that? There are these metrics, as we know. There are these packets, updates, yeah? They will come across and they will deliver information. What we're particularly interested in within these attributes is there is a network layer reachable information, yeah? So if we just have a quick look at these packets to see what there is, all right? I'm going to go back into my lab here, and I'll go on to here. Right, and this time I'm going to do enable. Fine. I'm going to do config T. Fine. I'm going to route to BGP 64513, 64513, and I am going to take out no network 192.168.3.0 mask 255.255.255.0. So that's it gone. What I'm going to do now, I will also shut down interface again, interface gig 03. I'm doing this so I can only receive information on gig 00. So I'm reasonably confident of getting something in Wireshark. Yeah, shut down. There it is. That's it. So it's broken in adjacency, all that and the other. It's gone down. So now on gig 00, I will start Wireshark. There's Wireshark started on gig 00. And hopefully we'll start to get some information coming through. We are. So now I'll get rid of that. Fine. Sorry, just need to drop that down out of the way. Right. So now I'm going to go back onto here. And this time I will do config T. Route to BGP 64513. Route to BGP 64513. I think that's right, isn't it? Yep. And this time I do a network. I'm going to put that network back in now. 192.168.3.0 mask 255.255.255.0. Fantastic. And then because I have now advertised that network, I have to encourage a route refresh. All right. So I'll just have a quick look at me running config to make sure I put it in okay. It's never 20 to 12. God, grave. So now there it is. I've got my networks 192.168.3 on my networks 192.164. So I'll do a clear IP BGP. That one, that has done a route refresh in effect. It breaks down the adjacencies and then builds them back up. And this time, if I now go into Wireshark, we should find, look, there is a BGP here. And we can see there are multiple messages. The keep lives are obviously just making sure that information is there. Fair enough. The update message, it is here. This is telling you about a change, as we know. And in that message here, if I click on the thing eventually, we can see again, we've got all the Fs, absolutely. We've got the length, it's an update message. Has any routes been withdrawn? Well, not in this case, no, they haven't. But look at this. This is a big deal now. In the path attributes, this is the kind of information that is exchanged. This is what makes BGP compatible between Cisco, Quagga, Bird. If we have a look on here, look. There's a slide coming up which makes play on this. These attributes, there is the origin. It has come from an IGP. The AS it has come from, 64513. The next hop, 201.1.2. This here, this multi-exit discriminator, we'll see about that in a few minutes. So I don't want to pinch me thunder there. Then you've got the network layer, reachable information. What on earth does that mean? Well, it means that actually somebody has triggered network 192 something, has triggered network 192.168.3. So this is where it all comes from. The updates, all of these messages are extremely important. And if we just have a quick glance at the route refresh capability as well. So in there it is again, look. All the Fs consistent amongst all the messages. Yeah, fine. It is a route refresh. It is a type 5. Fair enough. And then here it's telling us about the multi-protocol BGP. It sorts that. or the address fields. Okay, fabulous. Right, so that's what that slide was talking about. There is the network layer reachable information. There are the attributes, the AS path, etc. Now look, this is a big slide. These are the attributes themselves. There are some that have to be used. They have to be used. And these are they. They are well known. This stands for well known mandatory. So any update from any version of BGP must contain the origin. You've just seen it. It must contain the AS path. You've just seen it. And it must contain the next hop. You've just seen it. It makes sense. The systems need to know how to get anywhere. So these are all these attributes that I keep alluding to. The multi-exit discriminator, now you can see here, this one is optional. It is not well known, it is optional. You don't have to use it. Yeah, well-known mandatory, well-known mandatory, well-known mandatory. This is optional and you don't have to use it. It is also what they call non-transitive. That's what that means. If you compare that to these others down here, which are also optional, these are transitive. These will be kept as the system progresses, as the traffic goes through multiple ASs. The MED, the MED, the multi-exit discriminator, only goes to adjacent ASs. Then there are other types, well-known discretionary. Yeah, you can use it, but you don't have to. You don't have to summarize, but you can do. So these are important. Fine. The general attributes. This AS path here is a list of AS numbers traversed. All we have seen is the 64512 and 64513. But of course, there are hundreds of AS numbers. There are thousands of ASs. So the AS path is an attribute that keeps a list of ASs that have been traversed. This can then be analysed to see where the AS originated from, where the traffic originated from, sorry, or which ASs the data has traversed. Fine. The next hop, of course, is how to get to a network. I go from here, I go to a device over there, I need to know its next hop address, else I can't get there. Fine. And again, these are all specified in the BGP table. Fine. All of them. Here, we can now see this is the AS path. We have, or it's talking about the AS path attribute. We have devices here in AS1. This is the origin. And we are saying now, this is supposed to be the AS path attribute here. It's empty until, let me just show you, just bear with me. If I jump back onto my lab here, get rid of Wireshark. There it is. Go back onto here now. And I've almost forgot what I was going to do. Show IP BGP. We will, I've got onto the wrong device. But you can see here, the AS path now, as we speak here, is empty. Yeah, there is nothing happened. No information has progressed from VIOS1. Yeah, but when it does, what will happen, as information leaves VIOS1 here, it will put its AS number up here in 64512. So if we just have a look on here, you see what's happened. Show IP BGP. There you can see. So now VIOS2 has received some information from AS number 64512, and it is alluding to 11.11.11 network. Fine. You can see it's got the next hop IP address. Of course it has. Good grief. The information has got to get back from here. So that is 200.112. This is 200.111. And it's also, this means it's been originated by an IGP. Tremendous, tremendous. Like I say, I didn't realise the time had got to this time, chaps. So if you just bear with me. So in this AS path here, what happens, as the data egresses here, AS1 is put into the path. it will come across here. This device, this edge device in AS2 will say to the traffic, hang on a minute, you can't come in. I want to check your AS path to see if AS2 is in it. Well, of course it isn't. It's only AS1. Traffic will come in. It will traverse this AS. It will leave. As it leaves, AS2 is put in the AS path. It gets here. The device on the edge here at AS3 will say, hang on a minute, you can't come in. I need to check to see if AS3 is in your path. Well, it isn't. So in it comes, traverses and egresses. AS3 is put into the list here. Comes down to AS4. AS4, the edge device will stop it and say, hang on a minute, I need to check to see if AS4 is in your path list. Well, of course it isn't, and it allows it in. As it egresses, it puts AS4 into the path list. Fine. This then gets over to AS1. This edge device here will say, hang on a minute, I want to check your path list to see if AS1 is in there. Well, it is. And of course, it will drop it. The default nature is to drop it. But BGP being BGP, you can override it. But this AS path is a big old topic. Yeah. So there you go. The route selection. BGP will go through a process and pick what it considers to be the best route. And this is it. All right. These are the attributes. This is the highest preference, as it were. The BGP will check to see if something on the device has a higher weight. If it does, it will choose the path that has the higher weight. A weight is a way of saying, look, I want to use this interface. You can assign a weight to an interface. It is a Cisco specific thing, although Juniper have something very similar. But if there is no highest weight, it will drop onto which is only applicable to a router. If they are both, we'll say there are two interfaces. If both are the same weight, the process will drop onto the highest local preference. The highest local preference chooses an egress router. You have more than one egress router. So you can choose one of those by setting the higher local preference. Fantastic. If they're the same, so all devices don't have any preference, we then see where it was originated. If it was originated by the local router, remember that weight of 32768? That has been originated by the local router. It will try that one. Then, if it can't do that, it looks for the shortest AS path. Well, this is what's been happening in our system. There only is one, for goodness sake. But again, if they're the same, it will look for the lowest origin code. If they're the same, it will look for lowest med. If they're the same, it will look for the external BGP over iBGP. Why? They are different admin distances. Fine. And so it goes on and on and on. And sooner or later, it will get to a separator. There will be a device with the lowest neighbor router ID, because they're IP addresses. If there isn't, there will be a path with the lowest neighbor address, because they have to have an IP address. Absolutely. So, there you go. The local preference is here. The local preference in this case, there are two egress devices, and you can choose to set this one to 200, and the information will go this way. If this one was set to 300 now, and that's still 200, information would egress this way. So you can influence the point of egress by using the local preference. And it is AS wide. Yeah. This device knows that that's the best one. This device knows that that's the best one. This device knows that's the best one. So all information will go here, and it will go out into the big wide world. There is the AS path prepend. What you can do here, the AS path prepend, we have here, the system is leaving AS1, fine, or it's coming in from wherever it's come from, but it was going through then AS2, AS3, AS5. Fine, it's going this way, fair enough. Then we have another system here, which looks to have a longer line, yeah? This has three entrances here, three entries, I should say. There's three entries, AS2, AS3, AS5. This one has 1, 2, 3, 4, 5 pieces of information about the AS. And you might think to yourself, when you see this, why are there 4 4s here? That's unusual, but this has been done deliberately. we can prepend. We can put additional path numbers in. And this has the effect of making this path, it looks as though there are 1, 2, 3, 4, 5 entries, which there are, and this one only has 3. So now this, if I just jump back a slide or two, will choose the shortest AS path. Fabulous. So the AS path, they're important. Here's that metric. I said we'd come over it in a minute or two. This is optional and non-transitory. Yeah, it will only go to an adjacent AS. And here, there it is. This device, this system here, has 2 points of exit, multi-exit. Yeah, multiple exits. So the discriminator will choose the one with the lowest number here. Yeah. So you can influence how data comes into you on an interface or another. Marvelous. That's good stuff. And there we have it. So now there's a bit of a summary of the way information is propagated. External BGP can use the weight? No. Can it use local preference? No. Can it use the MED? Yes, it can, because it is going to this device here. Internal and the AS path as well, because of course the AS path goes from many systems. All right. Internal BGP, it doesn't use weight either, because it doesn't feature in BGP. It's just a way of delivering information. Local preference, IBGP, the metric, IBGP, and the AS path is also can be used in internal BGP. Absolutely. So what we've got now is another lab, but I just need to show you something else, because we have these things. We have route maps, we can have prefix lists, and we can have AS path filter lists. These are means of filtering traffic, okay? The prefix lists especially. They work with the update packets because, of course, the update packets delivers information on routes that have just entered the system, basically, and we can need to filter them. So this is how they work. We can have a prefix list here. IP prefix list called test is going to allow permit 192.168.00/16. This 16, this is a big deal. This is not a subnet mask. This means it's going to permit entries that have 192 here. Those 8 bits here can make 192, and those 8 bits can make 168. So that 16 is going to permit everything that has 192.168. It won't do anything else. It will just do that. Having put that prefix list in there, we then put it here. Prefix list on our neighbor, 10.1.1.1, we have a prefix list called test here, and we are going to bring in incoming data. Absolutely. The prefix lists are very, very powerful, as is illustrated here. This one will deny everything that is set to zeros, basically. You know, as simple as that. This next one here is going to permit everything that has the first 8 bits set to 10. Fine, that's fine. This next one is even better, because here we can use the subnet mask. So here, this prefix list is going to deny 10, everything with a 10, because it must match these 8 bits. And then here, this less than or equal to 32, that is referring to the subnet mask. Wow. So now you can deny everything that has a 10 and is less than 32. Less than or equal to 32, which is pretty much everything. You're going to deny every 10. Look at this one. Permit mask lengths from 8 to 24. Oops, sorry. Here, we are going to permit everything provided the subnet mask is between 8 and less than or equal to 24. You try doing this in an access control list, it's a bit of a task. Over here, deny everything with a subnet mask now of greater than 25, greater than or equal to 25. Permit all routes, permit everything, less than or equal to 32. Wow. Prefix lists are very, very, very powerful. A lot of people think they only just work on the subnet mask. They don't. They work on the proper prefix. Wow. There is this. There is this. we can filter on the AS path. The AS path has all of those entries of ASs it has traversed. So here we could now say remote AS number 2, 10.1.1.1 is in remote AS number 2. Fine. If it is, it is. We could then have a filter list number 1 and look here. This is going to say IP AS path. We are going to interrogate the AS path. We have an access list number 1 and we are going to permit only information which contains number 2, AS2. Then that's it, nothing else. That is the start of your AS path, and this is the end of your AS path. Oh, sorry. So we have an AS path access list 1, permit only information that has only a number 2 in the path. And then here, IP AS path access list number 2, permit information which only has a number 1 in its path. Then neighbor remote AS number 2, filter list number 1 in is only going to allow information that has come from number 2. Filter list number 2 out is only going to permit information from number 1. Does that make sense? Looks reasonable, doesn't it? So that's all good news. So that's it. I could show you that because we're just about done. In fact, that's it. So if I just show you that now in my lab, you okay for another minute, Holly?
Yes, I'm sure we can squeeze that in.
Yeah. The trouble is I shan't remember which device I put it on. But I do believe it's this one. Right, so of course the machine will take an hour or two to come on. Right, so if we have a look down here, what we should find, I hope, there. Look here, I have got something like this. I've got a route map for here, fine, there, and that's good news. And now this is the thing I'm looking for, chaps, this one here. There is IP AS path access list number 10, permit information that has come from 64513. So there, that is only going to allow information that has come from our green network, which is not unreasonable at all. Yeah, so that's fine. And so that would work there. Then I have a route map somewhere down here where I am saying route map AS path prepend in. I would be propagating my AS number to make it look longer. So there we go. So that's it then, Holly. How about that? That was exquisite timing, don't you think?
That was perfect. It's like you've done this before.
Good heavens, yeah. Last time I was nearly out of time as well. So, but there it is. So if I just bring that up there, there you go.
Perfect.
Finished.
Thank you very much, Richard, and thank you all for joining us for this 2-hour session. We hope you enjoyed this webinar. Remember, if you have any other webinar topic suggestions, please get in contact with us and we can look into this for you. We have another very informative webinar, Peering 101, coming up next week, so make sure you get yourselves registered for that and keep an eye on our events page on our website to find out where we are in the world and what free sessions we have coming up next. Thank you very much for attending our webinar, and we hope to see you next week. But if not, we'll see you again soon. Thank you.